Welcome. In this video I'll start discussing dissipation and things like resistivity and viscosity, which can be important in some cases. And so I'll discuss a bit the limits of ideal MHD, so when does it start to break down, what are some of the physics which is missing, and when does it become important. And then one of the typical cases is that there's a small region called a layer where this non-ideal effects are important. So it might be a very narrow current sheet which is formed, and in that current sheet you can't use ideal MHD, but the rest of the domain might be ideal. And so this kind of idea of a thin layer coupled to an ideal region is quite common. But I'll begin by looking at some of the limits of ideal MHD. And essentially it's a fluid model. It's assuming collisions are frequent, and so it's assuming the distribution function is close to Maxwellian. And this clearly is not true in most of the time in fusion plasmas. In fact, they're almost collisionless in many cases. And so we're assuming it's collision dominated when it's clearly not. So we're assuming it's collision dominated, whereas in fact fusion plasmas are nearly collisionless, especially in the core of the plasma, where we might want to study these large ideal modes. And so the problem is that empirically this model actually works very well. So ideal MHD works very well for experiments. It seemed to match the stability thresholds and growth rates in many cases and frequencies that are observed. And so why does ideal MHD work when clearly the assumptions are not correct? Well, one of the reasons is just that the dynamics which are not correct in ideal MHD are mainly the parallel dynamics, whereas the perpendicular dynamics is force balance, and is actually captured very well by the MHD model. And so the large dangerous instabilities we usually care about are dominated by this perpendicular dynamics. And so the parallel dynamics that MHD gets wrong is actually usually a small correction. And so whenever ideal MHD matters, it's usually correct. And in the cases which are small instabilities, it is where ideal MHD breaks down, when the parallel dynamics become important. So it's just sort of written here that the parallel dynamics which the model gets wrong are usually not important for things like equilibrium and large-scale instabilities. And the parts of the model gets correct, so the perpendicular force balance is such basic physics that J cos P is grad P, that ideal MHD gets most of that right. There are corrections, of course, so things like viscosity, and there are small corrections using FLR effects, but essentially the force balance in ideal MHD is the correct one. And so the parts that MHD gets correct are generally the important ones, and the parts that MHD gets wrong are generally small corrections. And so there is missing physics, and this can be important in some cases. And some of the missing physics are, so three examples are of viscosity, which we'll look at in a following lecture. This can be due to either collisions as the main effect. So this is either parallel viscosity or perpendicular to the field. There's also some terms called gyroviscosity, sometimes due to the finite Lamb radius. This is a bit different because it's not really a viscosity in the same sense. It appears like a viscosity in the fluid equations, but it doesn't dissipate any heat. So the force is always perpendicular to the velocity, so there's no dissipation, but it appears like a viscosity in the equations. There's also resistivity, of course, which can be important. Come across these for things like neoclassical tearing modes, wherever you have magnetic reconnection, you have resistivity can be driving that. And this is essentially friction or viscosity for the electrons, so electron ion collisions cause this. And then finally there's essentially resonances. So in lectures on the kinetic, we looked in the distribution function, these are where you have particular populations of particles which resonate with a wave, and this is really hard to capture with a fluid model. There are some attempts, so there are some efforts to have things like Landau closures, where you can try and capture things like Landau damping, which is a form of wave particle resonance which damps waves. And this can be very important in the core, but in general this is very hard to capture correctly. You can also have, of course, things like drift resonances. So in bounced orbits, so there's a period over which particles bounce, and that can also resonate with waves. and that also is very hard to capture with a fluid model, and you really need a kinetic treatment. So in this lecture, I'll briefly go through these two, and then there'll be follow-up lectures that go in these a bit more detail. So I'll start with viscosity. So I write down the ion momentum equation, because ions have most of the momentum. And so we're looking at things like viscosity. It's generally the ions that are important, although the electron viscosity does come into things like hyperresistivity. But for now, we'll just look at the ions. So we have the ion momentum. This U is the fluid velocity, remember? And then here we have just J cos B, the pressure. So this is the scalar pressure, and then we have the stress tensor part here. So remember, these two combine together to make the pressure tensor, and so this pi is a traceless. So the trace, i.e. the sum of the diagonals of this is equal to 0, and this is the viscosity, or the stress tensor. We'll see in a later video there's a quite complicated form for this for plasmas, or magnetized plasmas. But in general, for fluids, there's quite a useful form which is used in the Navier-Stokes equations, which is just that I'll put a minus sign here to make it convenient here, because there's a minus here. So we have a minus divergence of pi. So when pi is a matrix, so a rank 2 tensor, and we're taking divergence of it to get a vector, which is what the left-hand side is. And this is a combination of two things. So there's what looks like a diffusion del squared of u, where u is the flow velocity, so this is a diffusion of the velocity with some diffusion coefficient mu. This is called the dynamic viscosity. And then there's a second term, there's 1/3 here times mu, and then this is the compression term. And this term here ensures that if the plasma is compressible, so if divergence of u is non-zero, that this whole term is only non-zero if the fluid is being deformed. So for example, a rotation, so if you take a fluid element like this and then you rotate it, so you just like spin it around and you move it, translation and rotation, for example, this gives divergence of pi is 0 under translation or rotation. And in general, this is true for more complicated stress tensors. Is that if you're just moving the fluid around, then there's no stress. If you're, on contrary, if this term is actually deforming the fluid element, so you start with a fluid element which is it's called a square, and then deform it, so you have some kind of shearing motion, which kind of is like this, or stretching it maybe, so you're doing something like that. So if you're deforming or stretching the fluid element, then you have this divergence of pi. It's not 0 because you've got some kind of stress on the fluid, which is leading to a viscosity. And so adding this term here just ensures that this is true. Of course, if the fluid's incompressible, then this is 0 anyway, and it doesn't matter. Okay, so here we have dynamic viscosity mu in both these terms. This is related to another quantity. There's which I'll put this over here. So mu is dynamic viscosity, and we can write this as instead mu is rho times nu, where nu is the kinematic viscosity, and this is the one that has units of meter squared per second. That's the units. This looks like a diffusion coefficient. Mu has the mass in here, and so it's more like a force. So what we're going to do now is compare this term here, the stress tensor term, against this term here on the left hand side. And what we're interested in is to work out when is this large, when is this important. And essentially what we're going to do is compare this advection term to this stress tensor term and say if this advection term is much larger than the stress term, then the stress tensor term is negligible. Conversely, if they are similar, then clearly we can't neglect the stress tensor. So we're going to compare these two, we're going to normalize. I'm going to pick some typical velocities, so we can pick a velocity u0 is a speed, a length L, and that of course gives a time, which would just be the L over u0 is a typical time. And so we can normalize all the equations just by writing the normalized u is, which I'll put a hat on, is u divided by u0. So that just normalizes it all to around 1. We have the gradients can be normalized using, this is the gradient times by L. And so that is now dimensionless. And the whole equation we just write out. So we have the first term is basically like a u over L. Gives a time, 1 over time. And then we have u0, so we have another u0 squared. So here this gives us a du hat or dt hat. So the t hat gives an L of u0, and this u hat has another u0 here. So here the second term is probably clearer, so we have u squared, gives u0 squared, and a gradient is 1 over L. And on the other side we have the j plus p is grad p, which I'm not going to normalize here. And then we have the stress tensor term, which has a mu at the front. And it's differentiating u, and it's a second derivative, so it's u over L squared. So now everything is normalized, so the u's and t's and the gradients. So the only thing left are these constants at the front. And so you can divide through by u0 squared. We can multiply through by L and divide through by rho. And we end up with, so this is a dimensionless equation, and we're just left with this quantity here. This nu is the kinematic viscosity, so I've just expanded this here as rho nu, and then cancelled the rows on both sides. And now this is 1 over the Reynolds number, where Re is this, so it's u0 L over nu, and it's the ratio of the advection term to the viscosity term. So all written in terms of timescales, the Reynolds number is the ratio of the viscous diffusion time divided by the advection time. So it's the time it takes for momentum to diffuse compared to the time it takes for momentum to be advected or moved around by the velocity. And so if the Reynolds number is very large, then this viscosity term can be neglected, and if Reynolds number is small, then it can't be neglected. So at that point this can't be neglected anymore. So that's the Reynolds number. We will see there's a similar number for resistivity called magnetic Reynolds number. So look now, look at resistivity. And for this we'll write down the Ohm's law, just resistive Ohm's law for now. Come back to a more complicated form later. So this is E plus U cross B. We use the flow velocity is eta times J, where eta is the resistivity. Note that here we're writing eta as a constant, but in fact the things like the perpendicular resistivity is roughly twice the parallel resistivity. Eta parallel. And in general this can be a tensor, so this can be a tensor rather than just a scalar, but for now at least a scalar is fine. And then this is put into Faraday's laws. Then we have the dB by dt, then we have this curl of, and then here we have a u cross b. This is just curl of E is minus dB by dt, and then here we have the second term, which is this curl of eta j, and then we just use the pre-Maxwell form of j, so we ignore the displacement current, and we just have curl of b. And if we assume that eta is constant, then this term here becomes roughly, so eta over mu naught, so eta comes from here, just take that outside. The 1 over mu naught comes here, so we have a 1 over mu naught, del squared b. And this again looks like a diffusion equation. Well, this is basically a diffusion coefficient. So we can do the same thing as we did for the momentum equation. We now have a diffusion term and we have an advection term, and we can compare how large they are and compare one to the other using a typical length scale and a velocity. The only difference is now we need a typical magnetic field as well, and now we can write down the normalized form of the equation. So if dB by dt, this becomes just a b naught. The time gets normalized, so we have L over u naught for the time, and this gives a dB normalized by dt normalized. And then we have a curl, so 1 over L. So that normalizes the curl here. We have a u, which we normalize, bringing out a u naught, and then across b, which again I'll normalize here, so it's bringing out a b naught. And then here we have an eta over mu naught, 1 over L squared, and a b naught. And that normalizes both the gradients, the L and the b. Okay, now we have normalized equations with just these coefficients at the front. You can see here we have a b naught, u naught over L in both these terms here. So we'll divide through by that term, and we just end up with, you see again every term is normalized here, so it's all dimensionless except for this one parameter here, which is a dimensionless parameter, but it has all these coefficients in it. And this, like the viscosity equation, this is 1 over a coefficient we call Rm, and this is the magnetic Reynolds number. And just like the viscosity terms, so we can write this in terms of the timescales. So Rm is the ratio of the resistive timescale, so resistive diffusion. So it's time the magnetic field takes to diffuse a given distance, well, typical distance L, and the ratio of that to the time it takes the magnetic field to be advected by the flow velocity. This is also sometimes written as something called Lundquist number, which is just the magnetic Reynolds number with this u naught set to the alpha speed. So if we set u naught as the alpha speed, then we define S as the Lundquist number, so it's mu naught V A L over eta. So that's Lundquist number. So both the magnetic Reynolds number and the flow Reynolds number have a particular length scale, and so we can discuss these small length scales, and layers. So you can see these equations here. So we have coefficients like the resistivity, which is approximately constant given things like the fixed density or temperature. And we have typical flow velocities, and we all have a length here. So we can rearrange this equation and find a length. And what this is the length at which these two timescales become the same. And so if your scales are much larger than this special length, then obviously the resistive diffusion becomes very slow. And if you're very small, like much smaller length scales than this, then the advection timescale becomes slow compared to the resistive timescale. So there's a special length scale L, which makes this number 1, and the same for the viscosity term. Here, given a particular material, so a particular viscosity and a particular velocities, there is a special length which makes this 1, and so both these terms have a length scale. So for the Reynolds number, if the Reynolds number is about 1, then viscosity and the advection are of similar magnitude. And so we have that u naught L over nu, which is the Reynolds number, is roughly 1. And so there's a length scale, which is roughly the kinematic viscosity divided by the flow velocity. And this is typically very small. And same thing for magnetic Reynolds number. So if the magnetic Reynolds number is roughly 1, then the resistive term, so resistive diffusion, is roughly like advection. And since this term is just written as mu naught L u naught over eta, where eta is the resistivity, so this is about 1. We just rearrange this equation as that this is roughly eta from mu naught u naught, gives the typical length scale. And so these are small length scales at which the dissipation terms become important. So on long length scales, these terms are small and essentially get back to ideal MHD. So I'll call this one, so this is L nu, for example, for the viscosity, and L eta for the resistivity. And so if we have that L, the length scales we're dealing with, are much larger than L nu and L eta, then the dissipation terms are small. In some cases we can assume ideal MHD. And then at small scales we have to, if we have lengths which are comparable to these dissipation lengths, then we have to take into account non-ideal MHD. So if, on the other hand, so if L is roughly L nu or L eta, then non-ideal effects can be important. And this is what happens typically in these layer models. So we might have, say, a resonance where we have a particular surface, so that this is like if this is radius, for example, the Q, for example, is changing, and so here this might be where we have resonance, so Q is m over n, and so we might have currents, which for example might be very slow kind of oscillations, but then at the surface you can have very narrow layers, so something that looks kind of like this. So here we might have quite slow, small gradients, but in a very narrow region around this resonance surface. And here you might have very small length scales. So in this region here we might have very large currents, very steep gradients, and hence very short length scales. And this layer is where we might have non-ideal effects. And so over here we have small gradients, and so L is large. So L is sort of typical length scale, so this could be the length of the gradient length scale, and so these might be ideal. And here we have a small length scales, very steep gradients, and so this might be a non-ideal. And so those kind of layer models are where we solve for ideal MHD in most of the domain, but then in a very narrow region, a small layer around, say, rational surfaces, we solve non-ideal equations and take into account some of this non-ideal physics.